All right, hello. We're going to be covering polar and parametric curves and a couple of interesting things we can do with them today. Now, Professor Frizzell told me that not all of this was covered super in depth in class, so I'll be giving you a handful of formulas that'll be very useful to you today. There are a lot of formulas, so I'm going to spend more time just kind of giving those to you than actually doing like derivations right now, because that might take a lot more time. So I'm going to let's break this into two sides. We have parametric and polar, so I'll start with, we have parametric over here. So parametric is sort of the things we were looking at before, right? Where we have an x defined by t and then a y defined by t. So I'm going to begin with finding arc length. So I'm going to define arc length. I'm going to call this, so let's write it out this way. So we have the integral from a to b. And then we're going to do the square root of x prime of t squared plus we have y prime of t squared, and then we have a dt, okay? So this is really all the equation ends up being. And now, another thing we might be interested in is the surface area of revolution. So you remember in the past we did solids revolution. On today's workshop, we're not actually going to be finding the volume, but rather we're going to be finding the surface area of one of these parametric curves being revolved around an axis. So to do that, we actually take this arc length and we multiply it by either y or x, depending on which axis. So, like, to sum it up in just one word, if we're doing about the x-axis, we multiply by y. If we're doing along the y-axis, we multiply by x. So I'm going to do one thing that'll make my life easier, and I'm just going to call this whole thing over here, I'm going to call that S of t. And so if we have the surface area about x-axis, this integral ends up being the integral from a to b, and I'm going to make sure that's clearly like an x over there. That's going to be y of t times s of t dt. So I hope it's clear that in the actual thing, you're going to be taking this whole thing over here, right? So this actually, the surface area can be easier to compute. Maybe you can do some kind of u substitution, whereas this sort of thing might be a little bit harder. Okay, so coming down just one thing further, we have surface area about y-axis. And that ends up being integral from a to b of x of t, s of t dt. Hopefully that's still somewhat reasonable to read over there. Okay, so give me 1 second. We'll just be moving on to the polar stuff. Let me just make sure I covered everything correctly. Looks good. Okay, yes, so moving on to polar, just sort of like a quick recap of everything going on over there. So we're going to talk about our polar curves now. Hopefully that's still all in frame. Okay, nice. Okay, so polar curves are pretty interesting actually. There's these curves with this nice like circular sort of symmetry. And we generally define some things as the following. So we have that r is equal to the square root of x squared plus y squared. And let me just draw out this picture, because I think that'll make it a lot easier to visualize what's going on. So we say that this is theta, this is going to be x, this is going to be y. All right, x, y kind of makes sense. Using Pythagoreans, we say that this is x squared plus y squared. And this notation, we just call this r, right? So actually we can say that these two things are equal to each other in this case, right? And r can be thought of as this length here, and theta is this angle it forms. So r is defined as the square root of x squared plus y squared, and theta, in fact, actually, I can write this in a sort of nicer way. We can say that the tangent, tan of theta, right, is equal to, what do you guys think? Going to be opposite over adjacent, so it's going to be equal to y over x. So the thing I was going to write before is that you can also say that theta is arctan of y over x, but obviously arctan sometimes makes things a little bit more complicated. But those two are saying the same thing essentially. Two very important notes to make. Now, I'm sure you're wondering, what do we do with all this? So we're going to do similar things that we did before. One thing that you're interested in is sketching these curves. So the best way to do that is kind of like if you think back to how you first learned like curves in like algebra class, is you want to write out a table, right? You want to do values of r, and you want to do values of theta. So generally your thing will look something like the following. You might have r is equal to f of theta, and those are probably the kinds of things you're going to be looking at, right? So for some value of theta, hopefully this is still visible. For some value of theta, let me just check. Yes, okay, that's good. So for some value of theta, you get an r, and you just fill out this table, and it's very helpful. Now you need to be very careful when you're finding areas and lengths that sometimes you might get a negative r. So if you start getting negative r's, you need to be very careful, make sure that you're choosing a region, like a theta bound, that you're not getting a negative r, because you might actually get a negative length or a negative area in that case. But this is definitely one of those things, if it sounds a little confusing, it'll make a lot more sense with an actual example once we get into the workshop. So to not take too long, I'm just going to jump into our final couple equations. So from this whole thing, right, we can say that x is equal to r cosine theta. So I'll write that down. These are important formulas. We have x is equal to r cosine of theta, and we have y is equal to r sine of theta. Okay, these are very important ones. And then next up, we have our arc length, and this one is going to be given as the integral. I can choose a different letter, I guess I'll say from c to d, and we'll have the square root. And now this is some function of theta, right? So I'll have f of theta squared plus, now we have f prime of theta squared, and we'll put a d theta at the end. So this is our arc length equation now for polar coordinates. And then finally, for area, we're going to have just one last equation. I promise you, this is the last one. There's a ton of equations being thrown at you. I'm sorry about that. So for area, we have the integral from, let's just say again, for c to d, we'll have 1/2 f of theta squared d theta. So that's all this one ends up being. I know, tons of formulas. I wish we had more time to explain this right now, but this workshop's a little bit on the longer side. So maybe try and work through this stuff for now, see how this feels, and I think that covered everything. Thank you for checking it out.